I am Shanawaz. This is the 11th lecture on metric spaces. So we begin this lecture with the following definition. We say we consider a set A a subset of a metric space xt. Then a point in X is called an interior point of A if there exists some an open ball with center X contained in A. That is, if X we consider this open ball SXR, which is centered at X. This has to be a subset of A for some R positive. The set of all interior points of A is called the interior of A and is denoted by int of A or A to the power this small circle. This denotes the interior of A. So A interior is a set of all those points in A such that the open ball centered at this X, which is in A, this has to be a subset of A for some R positive. For some R positive. Observe that one can observe that this A interior is a subset of A because it contains the elements from A. Let us do the following theorem. A subset A, let us do this like this. Let A be a subset of a metric space X D, where D is the metric on X. Then first we have A interior is an open set, is an open subset of A. Second, every open subset of A is contained in A interior. In other words, A interior is the largest open subset of A. And finally, we prove A is open if and only if A is same as A interior. Now to prove this, first of all we have to show that A interior is open. Observe that note that an open set is a set for which is neighborhood of each of its points. In other words, so this is the proof of part first. So let us consider some point X in A interior. To show A interior is open set, we have to prove that any open ball centered at X, there X some open ball centered at X which is contained in A interior. Now if X is in A interior, then by the definition of interior of a set, then by definition there exists an open ball say S XR centered at this point X, which is contained in A. But we know that each open ball is an open set. Now this is true for some positive, for some r greater than 0. But SXR being an open ball is an open set, but SXR being an open set, each point of it is the center of some open ball contained in SXR. So this is the definition of an open set. And now SX is an open ball, hence an open set. So each of its point is the center of some open ball contained in it. So each point of it is the center of some open ball contained in SXR, and consequently also contained in A. So what we did, we first chose an arbitrary point X in A interior, then by definition of interior there exists some open ball SXR contained in A. Now SXR being an open set, each of its point is the center of some open ball contained in XR. Now as XR is subset of A, so any open ball which is contained in XR is consequently contained in A. So this implies that, therefore each point of SXR, therefore each point of SXR is an interior point of A. That is, SXR is contained in A interior. Thus X is the center of an open ball contained in A interior. Thus X is the center of an open ball contained in A interior. Now since X belongs to A interior is arbitrary, it follows that each X belongs to A interior has a property of being the center of an open ball contained in A interior. Hence this implies that A interior is open. Now part second, we have to prove A interior is the largest open subset of A. So let us consider, let G subset of A be any open set. Now to prove A interior is the largest open subset of A, it suffices to prove that G is contained in A interior. Let us choose to prove that G is contained in A interior. We prove that every point in G is contained in A interior. So let us choose a point, any arbitrary point. Let X belongs to G. Now since G is open, there exists an open ball. Say centered at X with a radius, suppose R positive, which is contained in G. Now G is given to be a subset of A. This implies, by the definition of interior of A, that X is an interior of A. Hence G is contained in A interior. So every open subset of A is contained in A interior. In other words, A interior is the largest open subset of A. Now to prove third, this immediately follows from first. A is open. If A is open, then each point of A is considered to be the center of an open ball contained in A. So if A is open, then definitely A is same as A interior. Conversely, if A is A interior, now A interior being an open set implies A is open. Conversely, if A is equal to A interior, then A is open, since A interior is open. Let us make an observation here. So one can prove it, but we do not give a proof here. This is a straightforward observation. So let us consider a function. Let f from x to y be any function. Let A is a subset of X and B is a subset of Y. Then f of A is subset of Y, is subset of B, if and only if A is contained in F inverse of B. Here we have this is x, this is y, and here this is subset A, and this is subset B of y. Now it is given that this A is contained here, so this is f of A. So if f of A is contained in B, so the inverse image of this subset, i.e. if we take the inverse of this subset f inverse B, so this will be a subset over here, and that subset has to contain A, otherwise this won't be possible. Similarly, if this is f inverse B, this is f inverse B. Similarly, if A is contained in f inverse B, then this f of A is contained in B. So this is a straightforward observation. Now let us do a proposition. Let x dx and y dy be two metric spaces. Let f from x to y be a mapping which is continuous then let f from x to y, let us do this like this, then I'm mapping f from x to y is continuous at say at A belongs to x if and only if and only if for every epsilon positive there x some delta positive such that the open ball centered at A with radius delta is contained in the inverse image of under f of the open ball centered at f of A and radius epsilon. Now this is what we had to prove. We are given that the mapping f from x to y is continuous at A belongs to X, then this is continuous at A belongs to X if and only if for every epsilon positive, there exists a delta positive such that the X distance between X and A is less than delta, implies the Y distance between f of X and f of A is less than epsilon for all so this is for all X satisfying this condition. Now if this is true, this implies this X belongs to the open ball which is centered at A and radius delta. So this implies this X belongs to the open ball centered at A and radius delta. Since distance between X and A is less than delta, so X has to be in this open ball, because if this is the open ball centered at A and radius delta, then this X has to be in this open ball, because distance between X and A which is this radius, which is less than this radius, which is delta. So this should imply this f of X must belong to the open ball centered at f of A and radius epsilon. So this is true for any X in this open ball. In other words, this implies that the f image of this open ball centered at A and radius delta, this must be a subset of the open ball centered at f of A and radius epsilon. Now by previous observation, this condition is equivalent to the condition this is equivalent to the condition this is equivalent to the condition that the open ball centered at A and radius delta, this is the subset of inverse image of the open ball, inverse image under F of the open ball centered at f of A and radius epsilon. So this follows from the previous observation. Next we are going to prove a theorem. So the statement of this theorem is like this: a mapping f from X to Y is continuous if and only if inverse image of any open set G in Y is open in X. So this is true for all open subsets G of Y. So this is same as to say that f is continuous, where f is a function from X to Y. This is continuous if f pulls back open sets in Y to the open sets in X. So let us prove this result. We first assume that f is continuous. Suppose f from X to Y is continuous. Let us consider an open set. Let G subset of Y be open. So we have considered an open subset of Y. We had to show that the inverse image of this open set G under F is open in X. We have to show that F inverse G is open in X. Since phi empty set and the whole set X are open, we suppose that since the empty set and X are open subsets of X, we suppose that F inverse G is neither empty and F inverse G is nor the whole space X. So if F inverse G is empty or F inverse G is X, then the result trivially follows, because both empty set and whole set X, they are open. Now let us consider that to prove that F inverse G is open, we have to prove that every point in X can be considered as a center of an open ball which is contained in this F inverse G. So let us consider that X belongs to F inverse G. So if this is true, then F of X must lie in G. Now it is given that G is open. Since G is open, there acts some epsilon positive such that the open ball centered at Fx with radius epsilon, that is contained in G, such that the open ball centered at this point f of x with radius epsilon, this has to be in G. Now we will use the given hypothesis that f is continuous. Since f is continuous at x, for this epsilon positive, there exists this delta positive such that this open ball which is centered at x and radius delta, this must belong to the inverse image of the open ball centered at f of x and radius epsilon. So this follows from the previous proposition, and this thing is contained in F inverse G, because this open ball over here, this is contained in G, so their inverse image, so the inverse image preserves the containment. So we are done in this case. Thus every point x of the inverse image under f of G is an interior point. Thus every point x of f inverse G is an interior point. Is an interior point. Is an interior point, and so f inverse G is open in X. Suppose conversely, f inverse G is open in X. For all open subsets G of Y, we have to prove that f is continuous. Let x belongs to X. For each epsilon positive, the set, I mean the open ball, as the open ball is centered at f of X and radius epsilon, this is open. This is open because every open ball is an open set, and so its inverse image is also open. S of f of X epsilon is open in X. Now since X belongs to f inverse S of fx epsilon, it follows that there exists some delta positive such that this open ball Sx delta, this is contained in inverse image of the open ball centered at f of X and epsilon with radius epsilon. So by previous proposition by previous proposition, it follows that f is continuous. So there is an analogous version of this theorem in terms of closed sets. So we can mention another theorem here, which states that a mapping f from x to y, from metric space x to metric space y is continuous on x if and only if inverse image of every closed set is closed in x for all closed subsets f of y. Proof. Let us consider a closed subset f of y. Let f subset of y be closed. Then complement of f in y is open in y, and hence by previous theorem, and hence inverse image under f of f complement is open in x. Note that this f complement is same as this f complement is same as this f complement is same as y minus set minus y set minus f. So this is the complement of f in y. Therefore f inverse f complement, which is equal to f inverse y minus f, which is equal to x minus set minus f inverse f. So so this is open set in x. Now if this is open set in x, which is same as f inverse f complement, so this is open in x, so its complement will be closed in x. So f inverse f is closed in x. Suppose conversely that inverse image under f of f, where f is closed subset of y, is closed in x. So this is true for all closed subsets f of y. So if this is closed in x, it is complement. Therefore f inverse f complement, which is equal to the x set minus f inverse of f. This is open, this is open in x. and so F inverse F complement, which is called F inverse y minus f, which is same as x set minus F inverse of f, which is same as F inverse of F complement is open in X. Since every open subset of Y is a set of the type Y minus F, where F is a suitable closed subset, it follows by using previous result that F is continuous. Since every open subset Y is a set of the type Y set minus F, where F is closed subset, where F is a closed subset of Y, it follows that F is continuous. This completes the proof.